So today I want to talk about a little bit about Harran's 2013 synthesis of Roseophilin. So it's a naturally occurring alkaloid. Um, they thought they could make it from this earlier synthesized starting material through some interesting chemistry. I think you guys could imagine where you could obtain this product from, probably just through Suzuki of this bond with this starting material and this one. But they obtained it from an earlier synthesis. So it starts with carboxylation of the Harran moiety. So they deprotonate here, and they with a zinc bromide with zinc bromide present, and that gives the organostannane compound, not the organostannane, the organozinc compound, which then is under palladium catalysis can be reacted with CO2 to give the carboxylic acid in this position. So after this, they make an activated amide using this methane sulfonyl benzotriazole compound, and they get an activated amide here, which under the presence of Lewis acid catalyst by titanium tetrachloride or titanium 4 chloride, they can react with this. Oh, didn't mean to do that. With this pyrrole derivative here, and getting this structure A. So after they have A, they spend a whole step phosphorylating this nitrogen atom of this pearl ring here, which will be used in a later step, one of the premier steps of this synthesis. So after this, they use organometallic Grubbs chemistry to give alkene metathesis in position 3. For product B. Then they react. Yes, they reduce the enone here. They start with an enone here, and they reduce it using palladium catalysis to an enol ether, a silyl enol ether, which they then hydrolyze back to the ketone to give product B. So this part from product B to this product here is probably the most important step of this synthesis, and it uses this equilibrium mechanism to allow for formation of this product, and we'll examine this mechanism here. So they start with this product. I put R, just to save space, I put these two aromatic groups as R. So first, in the presence of a base, we have some amount of this enol product here, so our enolate product here, which can react with this ketone here to give this intermediate product here. Since this oxygen atom is so close in proximity to this phosphine phosphonate group here, maybe it's a phosphoramide nomenclature, but this reacts with this here, and we lose the bond, the PN bond, to give a NO into O phosphenolidine transfer, and we end up with this product here. So this is favored because elimination can occur after this step in the presence of the base to give this product, which after acid hydrolysis can give back the pyrrole ring. So this is favored for two reasons. So we have first of all, oxygen phosphorus bonds are much stronger than phosphorus nitrogen bonds, and then after that, in the presence of the base, elimination occurs, and then it becomes irreversible. So we get out of this reversible area here, where it can go back and forth from here to here, and end up at a pretty much irreversible into O transfer, which then can eliminate to give this product, which on our other page is this one here. So after this, they use a stereoselective catalysis, stereoselective hydrogenation to give this product here. And you'll notice it's not exactly sharpless chemistry. They use an interesting 3-catalyst system. So they use Josephos, which is a ferrocene catalyst, along with rhodium catalyst. So you have Josephos and rhodium catalysis, which together make one catalyst, and then you have zinc triflate acting, zinc 2 triflate acting as a co-catalyst for this dual catalyst system here. So we get this product in a 67% enantiomeric excess and a good diastereomeric excess as well. So at this point, they lose some amount of their triisopropyl silyl protecting group on this to H, which is fine at this step because it's not necessary anymore in the synthesis. But they, instead of reporting the group as, you know, triisopropyl silyl or H, they just report it as R and then give you a ratio of 10:1. So saying just that, you know, they're continuing using this product, but it's a ratio of the triisopropyl silyl and just the hydrogen atom attached here. So after this, they use a really interesting Lewis acid catalyst to give a dehydration reaction. So this is some type of rhenium catalyst that's a Lewis acid, they say in the paper. And whenever they react this rhenium catalyst with in the presence of this, they dehydrate this as well as this position. They dehydrate this as this position to give this intermediate product, which they said was unstable at room temperature, so they just reacted it immediately with dry hydrogen chloride gas and presence of catalytic terbutanol to give an isomerization from this product to the final Roseophilin product. So overall, an interesting synthesis. The important step, I think, for this specific chemistry is the clever use of reactive phosphorus moiety and to give that N to O transfer here. To give the N to O transfer. I think this is probably the most interesting part of the synthesis. Maybe that rhenium catalyst at the end was interesting too, but this transfer here just really kind of utilizing the thermodynamic fact that, you know, PO bonds are practically unbreakable, whereas PN bonds are less stable, and attaching that in an earlier step in the synthesis where, you know, just reading straight through it, you wouldn't realize how important it is later on. So, and of course, interesting uses of organometallic chemistry, as you'll often see in modern synthesis. Grubbs chemistry is used in almost every natural product synthesis these days. I think Negishi coupling this would be, so with the organozinc compound. Of course, Lewis acid catalyst. It's hard to call that organometallic chemistry. Really interesting rhenium catalysis, you know, given the dehydration of this oxygen and this hydrogen bond here, or yeah, C to H bond here, and of course using modern organometallic catalysts here for this asymmetric hydrogenation, which is important these days, sharpless chemistry. Overall, pretty good yields as well. You see 79%, 85%, 71%, good all the way down to this last few steps where they got a 32% yield over, I think, for these two steps here. So they got the product as a hydrochloride salt, which of course they can just basify to get the final product.